Welcome to lesson 2-6, logarithmic functions. The objective of this lesson is to show that logarithmic functions have the multiply add property and find particular equations by means of algebra. So before anything else, we start by the definition of a logarithmic function. So what is a logarithmic function? By definition, the general equation of a logarithmic function in its untranslated form is y is equal to a plus b log c x, and this is called the base c. Notice that your base is c. Okay? Where a, b, and c are constants. So they are real numbers and they are constants. And your b should not be equal to 0. And c should be greater than 0, and c should not be equal to 1, as referred to the exponential functions, wherein you have y is equal to b raised to x. Okay? Now your b here cannot be equal to 0 and 1. Okay? And what else? Since our logarithmic function is actually the inverse of the exponential function, so they must somehow, what do you call this? They must somehow share the same properties and similarities. But the domain of the logarithmic function is all positive real numbers. Okay? Whereas the domain of an exponential function is all real numbers, negative and positive. Okay? So in the transform function of a log function is y is equal to a plus b log c x minus d. And notice that a is the vertical translation. So if you may recall, a is the vertical translation. It is translated a units upwards. Okay, depending on the sign of a. If a is negative, then it would be translated downwards. So a units below the original function. And b is the vertical dilation. Okay, and d is the horizontal translation. So it would be translated d units to the right, depending on the sign of your d. If your d is negative, then it would be translated d units to the left. So remember that log, and this has been taken into consideration in the last lecture for 2-4 and 2-5. Log stands for base 10, okay, logarithms. And when you see the word ln, okay, is it even a word? It's an expression, okay, ln, then it stands for base e, logarithm. So just taking a note that if you see the word log, these are for base 10 logarithms, or the common logarithms, okay? And if you see the word ln, then these are for logarithms with base e, okay? So base e log. Okay, let us now have some illustration of the logarithmic function vis-a-vis the inverse, which is the exponential function. So starting with our original function, the exponential function y is equal to 2x. Y is equal to 2 raised to x. This is the exponential function. You could see that along the line of reflection, okay, y is equal to x. This is the line of reflection of the exponential and the logarithmic function. Then y is equal to 2 raised to x has a certain inverse, which is equal to x is equal to 2y. Okay, and we have already proven that in the in the previous discussion. So y is equal to 2x has domain which is equal to the range of your exponential function. At the same time, your range here is equal to the domain of the inverse function. Okay? Now, this inverse function, as you can see, the domain is all the positive real numbers. Okay? So these are these are positive real numbers. Whereas for your exponential function, the domain is all real numbers. Okay? But the range of your exponential function is all positive real numbers. So all y greater than 0. And the range of your inverse function is all real numbers. So see how they are compared to each other, right? And the inverse of the inverse of the exponential function is most commonly referred to as the log function. Okay, so this is logarithmic function. Which is similar to the exponential function x is equal to 2y. Okay? Now let us take another example. We have here the function y is equal to e raised to x. And we have y is equal to ln of x. And if you use your grapher, okay, you could see that the y is equal to e raised to x has a pattern which goes like this. The behavior is like this. And it is an exponential function that has a domain also of all real numbers and a range of all positive numbers. And for y is equal to ln of x, this is just the inverse of your y is equal to ex. Okay? And there's another example. Let us have the base 10 exponential function. So y is equal to 10 raised to x. This is y is equal to 10 raised to x. And this one is y is equal to log x. So your log x has the base 10 logarithms. Okay? The y is equal to log x has its base as 10. Whereas the exponential version is the base is 10 and it's raised to a certain exponent x. Okay? So these two are inverses of each other. Okay? So, and also notice that each of these functions, y is equal to 2x and x is equal to 2y, or log, this is also, just to take note, this is also equal to y is equal to log 2x. Okay, so note that the line of reflection is always y is equal to x. This is where they reflect. Okay, this is where they mirror their behaviors. And so let us now define what a logarithmic function is in terms of its property multiply add. Okay? In the previous lectures, we discussed about some properties of functions, such as, what are those properties? We have the linear function, right? The linear function, the exponential function, the power function, and the last one is the quadratic function. Okay, and we've showed that for linear the property is add, right? Add. For exponential, it's add multiply. Okay, this is add multiply. For power functions, this is multiply. And for quadratic functions, these functions have properties of the constant second difference. Constant second difference. Okay, now here goes another function, which is the log function. And in addition to this bank of functions, the log function, or logarithmic function, exhibit the multiply add property. Okay, so this is multiply add. So it's like as you can see, it's the inverse of the exponential function, because the exponential function behaves with a property of add multiply, right? But now our log function, which is the inverse of the exponential function, has multiply add property. So let's begin with introducing some tabular values, okay, for x and y, and we always do this. Okay, so let's say I have my values for x and my values for y, and my values for x are 6, 18, 54, and 162. 6, 18, 54, and 152. And my values for y is 1, 2, 3, and 4. Okay. Now notice that my x values have a certain property of multiplication as compared to the y values, which have a property of addition. Now in the y values, we begin with the y values because they are much easier to evaluate using the I, okay? So we have 1 going to 2, this is an addition of 1. 2 going to 3, this is an addition of 1. And 3 going to 4 is an addition of 1 again. And for the other part, for 618, notice that this part here is multiplied by 3. So 6 times 3 equals 18. 18 times 3 is equal to 54. 54 times 3 is equal to 152, right? So notice that if we interchange the variables, okay, the values for x and y, we could easily see that x is an exponential function of y. So it has the notation x is equal to b raised to y. And we could see that x is equal to 6, or rather, we have, look, the first value of x is 6. So that will be broken down into 2 times 3. Okay? So since it could be broken down into 2 times 3, then we could see that for each of the succeeding values for x, it is always multiplied by 3. So therefore, our basic function would be 2 times 3 raised to y, right? And we could solve the equation. We could solve the equation by getting the algebraic computations for this one. But in order to get that, okay, we would be needing points. So this is our equation, and we have taken it out of consideration, okay? So in this case, if we want to get that equation, what we're going to do is to consider 2 points, x and y. So point, let me erase this. This is not needed. Okay. So I have my first point as 6 and 1, and another point, point 2, is equal to 18 and 2. And I am postulating that x is an exponential function of y. Therefore, x would be equal to ab raised to y. Am I correct? Okay. That gives me the starting point in solving for the equation. So if my x is 6, so that gives me 6 is equal to a, b, and my y is 1. This is the first equation. And if my x is 18, so this is 18, is equal to a, b, 2. This is the second equation. Okay. Now to solve this, we're going to get the ratios of the second and first. So it would be 2 over 1. And 2 over 1 will give us, what will it give us? So 18 over 6 is equal to ab squared over ab. And I could cancel out my a, okay, and b. So this will leave me with 1b. So b is equal to 3. Okay, and so I have my b now. So my b is 3. How about my a? So if I substitute my b to 1, so in equation 1, 6 is equal to a, and my b is 3. So my a would be equal to 2. Am I correct? So I get my a as 2. So now I have the equation x is equal to 2 times 3 raised to y. Now let me make this clearer. Okay? So x is equal to 2 times 3 raised to y based on algebraic computations. Okay. Now this equation can be solved for a y as a function of x with the help of logarithms. So what are we going to use here? Are we going to use the natural log or the common log? So x is equal to 2 times 3 raised to y. So since this is an exponential function, we can use logarithms. And in this case, we are going to use the natural logarithm of both sides. So meaning we're going to set both sides but to the natural logarithms. So this one becomes ln of x, and this one becomes ln of 2 times 3 raised to y. And having this, so ln of x would be equal to ln, this is a product, okay, so we can separate the 2 by adding their natural logarithms, so ln of 3y. And this will give me now ln of x is equal to ln of 2 plus, this is a power raised logarithm, so we use the power rule, and that will give me y ln of 3. And we are solving for y here, okay? We're solving for y. So indeed, what we're going to do is to rearrange. So y ln of 3 plus ln of 2 is equal to ln of x. And y ln of 3, because I want to express my left side in terms of y, so this becomes ln of x minus ln of 2. So therefore, dividing both sides by ln of 3 to simplify, we have ln of 3, we have ln of 3. So we could cancel our ln of 3 here, and this will give us ln of x over ln of 3 minus ln of 2 over ln of 3. So this becomes, what is the constant here? We could separate the ln of x over ln of 3 by 1 over ln of 3, and then ln of x minus ln of 2 over ln of 3, and solving them with the use of a calculator. So what is 1 over ln of 3? So 1 over ln of 3 will give me 1 over ln of 3 will give me 0.91023, etc. Okay, ln of x minus ln of 2, natural logarithm of 2, divided by natural logarithm of 3 will give me 0.6309 infinite series. Okay, and this equation is a logarithmic function with a is equal to, what is our a here? Our a is, okay, how do we determine our e or our a? Based on the definition, our definition for the transform function of the logarithmic function is a plus b log c. So let us rewrite that. Y is equal to a plus b log to the base c of x minus d. Okay, so what is my a here? Based on that definition, my a would certainly be so my a is equal to negative 0.6309. What's my b? What's my b? My b is equal to this one, okay, 0.91023. Okay, so therefore, if you see a table, a tabular representation which has a property of multiply add, then that's basically a logarithmic function, and you could get the expression for y by using the natural log, okay, to express the individual logarithms of the given exponential function of x, which is in terms of y. Okay, so this is an introduction of the logarithmic function and its property, which is called multiply add. And on the succeeding lessons, we're going to deal with the computations of the equations of logarithmic functions using the multiply add properties. So thank you for listening and watching, and have a nice day, everyone.